There's a close connection between the idea of continuous vector functions and space curves. If f, g, and h are continuous real-valued functions on some interval which we'll identify as I, then the set of all points x, y, z in the space where x equals f of t, y equals g of t, and z equals h of t, and t varies throughout this interval I, is called a space curve. Now, these values or these functions where x equals f of t, y equals g of t, and z equals h of t are parametric equations of the space curve, and t is the parameter. This, I think you will agree, is a natural extension off of what we already have come to love and adore as your basic parametric equations. It's just that now we have a vector, and each component of the vector is defined by a function. And this vector, the tip of the vector, actually traces out this curve in 3 space. Now, we can think of a space curve as a particle that's traveling through space, whose position at any time t, where obviously t is in the domain, is defined by f of t, g of t, and h of t. As I said a moment ago, the vector function r of t is actually then the position function not position function, I'm sorry. This is a vector. It's a position vector of the point P, which is defined by the coordinates f of t, g of t, h of t, with the tip of that vector function r of t actually is simply tracing out the path of that particle. Sketching these guys can be pretty difficult. Let's do a quick example where we're going to try to sketch this particular space curve. Actually, well, let's just walk through this for a minute. I'm going to try to visualize what the space curve is going to look like, and I'm going to let Maple do it for me, because these can be extremely difficult, especially if you lack artistic ability such as myself, to actually draw with these space curves in 3 space. It's extremely difficult to do. But let's take this component by component and think about what's going on. We're thinking of this as the x, y, and z components. So the x component, if I think of this as x and this is t, as t varies, cosine, or x is actually equal to cosine of t. So when t is 0, because I'm going to go from 0 to 2 pi, x is 1. So basically, from 0 to 2 pi, it's going to look something like that in terms of what's happening on the x-axis. So I know in parametric terms, I'm going to be going back and forth on the x-axis. Now, y is t squared. So if I do something like this, here's t and here's y. T squared is going to look like this, but from 0 to 2 pi, it's going to be half a parabola. It's going to look like that. So again, as t gets bigger, rather than moving back and forth between 0 and 2 pi, y is going to increase at this rate, at a parabolic rate. And obviously, the last one where z is just equal to t, that simply means that z is going to be constantly increasing, because I'm going from 0 to 2 pi, and this is a linear function. So let's jump over to Maple real quick. And I need to set up Maple to do this, so I'm going to tell it with student, and then I need vector calculus, because that will load the packages that I need. Whoops. Spelled student wrong. Let's fix that real quick. There we go. And now I'm going to tell it to simply give me a space curve. And I'm going to give it the components. We have cosine of t, t squared, and t, and I'm going to tell t to go from 0 to 2 pi. And there is my space curve. Now I'm going to add to this thickness equals, I'm going to go to 4, see what that does. Yeah, it gives me a nice thick curve. And I think I'm going to stick in here some axes information real quick. And let's label it. Oops, too many of those. Okay, so now I have an axes working here for me. And let's see what we got here. Now here's the x-axis, y, and the z using the right-hand rule. So let's take a look and see what happens with x. Let's see if I can hide the y-axis and just kind of get, well, there's x, you can tell. But there's 1. Let me flip it this way. Look at the xy plane. And I'm not going to spin it all the way around because sometimes I get lost trying to spin these things. But anyway, here's x, here's 1, and there's basically that's a cosine curve. So I'm good there. And then I'm going to take a look at the YZ curve or plane, and I can see that I have this parabolic shape sort of going, and then Z is obviously constantly increasing. So in general, I had a good idea what this thing is actually going to look like. You can see in 3 space, where this is the x-axis here, y-axis, and z. X is moving back and forth like cosine would be. Y is actually moving up in a parabola, and z we're moving, well, on the y-axis anyway. It is parabolic in general, and z is just constantly increasing. So anyway, there's my space curve. I think you can very easily see why this would be difficult to try to hand draw. When you hand draw in any one of these positions, you kind of lose detail. So you really need something like Maple or some kind of software so that you can manipulate it and get a good idea of just what is going on.